All right, well, good evening, everyone, and welcome to another virtual star party. I'm Dr. Billy Teets, and I'm the director of the Vanderbilt University Dyer Observatory. So tonight we have another great program. We've got some of our regular presenters, and we've got some new ones as well. So we're going to have a lot of different topics that we're going to cover tonight. So we've got some folks from here at Dyer Observatory. We've got representation from Bays Mountain Park and Planetarium, the Barnard Seaford Astronomical Society, the Memphis Astronomical Society, and also Rhodes College in Memphis. And then last but certainly not least, our friends up north from McGill University are joining us here tonight as well. So a big thank you to our presenters for taking the time this evening to put on another great program. I also want to thank a couple of people working behind the scenes tonight. Helen Morissette, one of my colleagues at the Vanderbilt Dyer Observatory, is going to be helping us, and Brian Smokler of VU News and Communications is also making sure that our stream is getting out to you all tonight. So a big thanks to all of them. If you didn't see it in our pre-programmed slideshow, there are a couple of resources that you'll want to check out on the homepage of Dyer Observatory. So first of all, we've got a couple of star charts. One is a really nice color version that looks great on your smartphone or your computer, but if you'd like to print it out and go outside and use it to find objects in the sky, we also have a nice black and white version that's not going to eat up all of your printer's ink. And we've also got a really nice calendar that my colleague Alex Rockefeller painstakingly put together. I mean, this is chock full of images, information, all sorts of stuff. So we're highlighting events that are going on in the sky above us, and we're also highlighting historical events as well. So be sure to download this as well. All of this is located at dyer.vanderbilt.edu, but we'll be having monthly star charts and monthly calendars up on our website. So be sure to check back. So before we start our program tonight, I have a few announcements. First of all, if you have questions as we are going through the program tonight, please post those in the chat on YouTube, because we don't want to just sit here telling you information. We want to get your questions. We want to interact with you all. So don't be shy about asking questions. Also, if there are topics that you would like us to cover in one of our future shows, please let us know about that. We're always open to suggestions. Maybe it's a specific topic, or maybe you want us to try to observe a specific object. Again, we love taking suggestions, and we love hearing from you all. So also, if you didn't see the reminder email that was sent out this morning, one of our activities in a little bit is going to involve toilet paper. So make sure that in the next 20, 30 minutes or so that you grab either a pen or a marker. You could use a pencil, but a pen or a marker works better. And about 6 feet of toilet paper. You want 6 feet in a continuous strip there. If you grab more, that's fine. But just make sure you have that, because we're going to be doing an interactive activity. So I'm not going to spoil the surprise, but I think you'll enjoy it. So with that, let's go ahead and jump right into our first presenter. So if you've been to these star parties before, then you'll recognize this gentleman. Mr. Adam Thans of the Bays Mountain Park and Planetarium is going to be our first presenter for this evening. So Adam has been into astronomy since he was 12 years old. He got his master's degrees in astronomy and education at the University of Florida. And then he ended up at the Bays Mountain Park and Planetarium starting in 1992. And ever since then, he has been educating folks and showing them the wonders of the night sky. So without further ado, let me turn it over to Adam.
If you can hear me, my video is locked out by the host. Sorry, folks.
Hold on 1 second there.
There we go. Okay. There you go. Good. I'm glad you could hear me. So, all right. Thank you, Billy, for that nice introduction. And I'm Adam Thans. I'm the planetarium director at Bays Mountain Park and Planetarium in Kingsport, Tennessee, all the way in the eastern corner of Tennessee, right up there in that little pointy bit. And we have a beautiful park out there, one of the largest city-owned parks in the world. We have 3,650 acres, and it's a nature preserve, so it's all wooded. There's a lake that's about 44 acres or so, and we have animal habitats, and of course we also have a planetarium theater that's actually being refurbished right now, that will reopen soonish, and we're excited to share the night sky, astronomy, and space education to everybody. So let's get started. So being a planetarian and also an astronomer and an educator, I feel like, base information, basic instruction, what's really important to learn before you get into the more difficult topics. And so I'm going to focus on that tonight. Unfortunately for all of us, we're all clouded out. And so we're not able to show the actual real night sky through our telescopes. So I've got a presentation set up where we're going to be learning about time, the seasons, and precession. You might have heard of all of those. So let's start with time. Okay, so time, you just look at your watch or your phone and it's got the time on there. But there's a process as to how do you figure out what the time is. And so that's what we're going to cover. What you see right now, you should see me in the corner, our logo on the other side of the other corner, and then in the middle you're going to see a fisheye view of the entire daytime sky. This is actually set for today at in the middle of the day, and I'm going to ask rhetorical questions to all of you. I know I can't hear you answer, but I'll give you a pause. I'll give a pause to let you answer, because I would like for you to actually say the words, and then I'll respond. And so if we're in the middle of the day, what do we call that? What is the middle of the day called? There's a name for it, and that's right, it's noon. So we call that noon. Well, guess what? Everyone has their own personal noon. No matter where you are, it's yours. Nobody else's, unless somebody's right next to you. And the reason being is, in order for noon to occur, first we see in our image, we see the sky, we see the sun up in the sky. But what we're really looking at, what makes it noon, is this. We see now some letters and a line going across. And you see this line going through the north and south, and also through that Z. That Z stands for zenith, which is the point directly above your head. Not mine, not anybody else's, your head, that's your zenith. And that line that goes north-south and through the zenith as well is called the meridian. That meridian divides the sky into two parts, two halves, the eastern side and the western side. And we can see in our picture that the sun is on the meridian. So when the sun crosses the meridian, that is noon. You've also heard of time zones. The whole world is divided into 24 time zones. And in the United States, it was actually established to be used because of the railway system back in the mid-19th century, because every train station had its own time because it was based on its own local noon. And there were times when you could actually travel on the train and go backwards in time, depending on if you went east or west. And so it got very confusing. And so they made time zones so that everybody in a zone was at the same time, even though your true noon might vary. And it varies longitudinally as you go from east to west, either way. So this is time, and noon is established by this. And if you stick a stick in the ground that's sticking up, and you'll notice the shadow, and you'll notice over time that that shadow passes along, because what's happening? The sun's not actually moving across the sky. It's not moving. Something else is. What do you think? I bet you can tell me. Yeah, that's right. It's the Earth. How is it moving? I think I'm hearing a couple of different words. I'm hearing rotating, I'm hearing spinning, I'm hearing revolving. Well, actually, revolving is orbiting the sun, where you go around something, but it's rotating, spinning like a top. And so it makes it look like the sun rises in the east, crosses overhead, crosses that meridian, and sets in the west. And Viano next, one of the next speaker is going to be talking about the sun on the horizon and archaeoastronomy. It's going to be cool. It's going to be great. And it's going to tie into this directly. But when it's doing that, it looks like it's making an arc across the sky. Now, what about like time itself? Okay. I've brought up a couple of words and some letters. AM and PM. We all have heard of those. Did you know they actually mean words? Anti-meridiem or post-meridiem. And that means that it's either before or after the sun crossing the meridian. Simple as that. So your morning is before noon, evening is after. And if you generically divide up the sky, or the time of daytime, from say 6 a.m. to 6 p.m. and not worry about variations, you can tell the time. And that's why sundials were so popular, obviously, a long time ago. Most people couldn't afford a clock even, but sundials, very simple, to stick in the ground or stick in the wall, and the time is painted on the wall there. And if you're in Europe, you see them all over the place. So time is based upon the sun's position in the sky and the Earth's rotation. Next, we're going to be learning about how important the Earth's rotation is, because we're going to be looking at seasons. Here we have our seasons. Okay, what do you see? We see the sun at noon. Notice those lines. We have two more lines, and we also have the stick drawings of constellations. Just ignore those for now. South is to the bottom in front of us, east and west. East is to the left, west is to the right, north behind us. We have our meridian line, but those two other lines, the blue line that's going from east to west, that's the celestial equator. That's the Earth's equator projected out into space. The other line that's very tilted is the ecliptic, and that is the apparent path the sun makes across the sky throughout the year. So the sun follows this, apparently follows this pathway across the sky, and it goes through certain constellations. Well, even though this is a daytime view, you might recognize some of the constellations there. Now, I know you're not going to see my arrow at all. I don't have a way of doing that, unfortunately, but from the right, you're gonna see just to the right of the sun and down below a little, that's Virgo, and then we go into Pisces as we go towards the left. If we go a bit more, we see Taurus, and then Gemini's off to the edge there in the upper left. So it's going through the zodiac constellations. That's why the zodiac is so well known. It has no effect upon us, but that's where we see the sun passing through. This is spring, which is in 1 week from now. So we're not quite there yet, but in a week, the sun will be seen to move along its ecliptic and traveling from below the celestial equator to above the celestial equator. So here is spring. Now let's go to the next season, which I know you know, summer. Did you notice something? The sun's position is higher up. It's not at the zenith. Can you see? It's a little below, because for East Tennessee, the sun never reaches the zenith for us. But that would be the highest position on noon, and it's almost straight overhead. And that is why it is hot during the summer. It is not because of us being close. We're actually the farthest away. We're farther away from the sun in the northern hemisphere summer than in the winter. But it's because the sun's altitude is very high. We have a lot more sunlight, a lot more hours of sunlight. The sun is more direct, beaming down on us as opposed to a sharp angle from a low horizon. And all of those things warm things up. But did you notice that the ecliptic is now higher, more towards the zenith than the celestial equator? Now let's go to the season after fall. And we can see that it's now back on crossing the celestial equator. This is fall. We call spring and fall equinoxes. Equinox, equal night. So that means that it's 12 hours daytime, 12 hours nighttime. So that's where those names come from. Equinox, equal night. The solstices are for summer and winter at those extremes. So we have our summer solstice. Right now we see fall equinox. And I bet you can guess about where the sun will be seen in the winter, which is the next season. Is it going to be higher in altitude or lower in altitude? And I think you know the answer. It's going to be lower. This is why it's colder in the winter. So the sun's this is noon for winter for the Tri-Cities. Very low sun means very steep shadows, very little light, not as many hours of light of daytime. And so that's why it's colder. So, and then going back to spring, and I'll flip through these quicker again so you can see kind of how it goes up and down, up and down. The Earth is tilted on its axis, and so it makes it look like the sun is going up and down, but it's because we are rotating and orbiting the sun, but because our tilt of our axis is always pointing to the same part in the sky. So that's why we see the sun higher and lower. So we have here summer, fall, winter, spring, fall. I'm sorry, summer, fall, winter, spring again. So the Earth's axis is tilted. And so that's why through the year, every 4 months, we see the sun higher and lower. Now let's go to a slightly harder concept, and it's called precession. Precession, you've probably seen this as a child, not in the sky, but playing with a toy. And if you've ever played with a top, you spin the top and it's spinning. As it's still spinning but slows down, it starts to do this wobble. It's still spinning, but it does this wobble. You probably noticed that. That's called precession. Guess what? The Earth is a gigantic top, and it just keeps spinning around like that, and that is precession. The Earth's precession takes 26,000 years. So what's the effect? Okay. Watch what happens. We're keeping to the vernal equinox. Actually, no, this is the autumnal equinox. I'm sorry. But notice the constellations. Notice that they're shifting. We're going through 26,000 years. Notice how those constellations, which are the zodiac constellations, look like they're traveling along the ecliptic, that kind of orangish tilted line there. And so because the Earth has not only the tilt of the axis, but it also has that wobble, it is pushing those, it makes it look like it's pushing those constellations round and round. And so let me pause that for a second. In fact, let me go back to the beginning where you see Leo in the middle there, close to the intersection, and the Big Dipper almost near the zenith, up a little higher than the center point. Now I'm going to show you this picture, this next one. You see that circle? That is called the precession circle. And I know about my time, so I only have a few minutes. But notice where it says NCP, the North Celestial Pole, it's right next to the end of the Little Dipper there. That's Polaris, the North Star. But that also means that the Earth's axis, which currently is pointing near the North Star, doesn't in its 26,000 years, and it travels along that circle. And so we see different stars depending on how many thousands of years ago in the past or future. And it just goes round and round on that circle. And so if you go back many thousands of years or in the future, their North Star is different than ours, unless you were 26,000 years ago. Now I have a different view of the effect of precession, and I hope that it's not going to be confusing. And what we're doing now is that we're precessing, but you see Leo there, and the tail star of Leo I've kept on the meridian line. And so now you're seeing the effect of that wobble. You see how the sky is doing this kind of a wobble. It's going tilting, and then it comes around. So you can imagine, like, if you were looking at the night sky and then kind of rotating your head like that, and that's how the sky would look. And so that's the effect of precession. And so it changes where the sun would be for certain seasons. Remember, the seasons are based upon, is the sun at the highest of the ecliptic away from the equator? That would be the summer solstice. Is it crossing the celestial equator, which would be either the spring or the fall, depending if it's going up or down, that kind of thing. And so the seasons also, there's a change in those as well. And of course, this takes 26,000 years as to what constellation we would see in the background. Let me stop that. And I'm going to go back. I know I kind of went through that pretty quickly. I want to see if there's any questions of anybody.
Actually, Adam, got a couple questions here.
Good.
So, so I'm just trying to read them here. Oh, so for precession, does the moon help with precession, or so does it amplify the effects of precession, or does it kind of hinder precession, or does that have any effect on the Earth?
That's a good question. Yeah, that's a good question. As far as I know, no. All right. Actually, I'm going to take that back. It depends on how far back in time you go, right, Billy? Because, okay, the moon used to be a lot closer to the Earth, because our best understanding of where the moon came from is that there was a collision of an ancient version of the Earth with an object about the size of Mars. And with that collision, destroyed the Earth, but most of what was the Earth and some of the other object, came together. And then the moon, the material that made up the moon, went in orbit around the Earth, but it also had some more of whatever the other object was. And the way we know this is by the geology of the moon and the Earth. The moon, if it formed with the Earth, should be identical in components and in ratios, but it's not. It's a little different. And so that's why we think there's this mix. Also, even through mathematics, we can actually calculate the effect of the moon. And we know for a fact that with physics, that the moon was a lot closer to the Earth. It went around the Earth faster. But because of tidal effects, tides, not only does the moon affect tides on Earth, and especially things that are easy to move like water, but there's also a tidal effect the other way. We have a tidal effect on the moon. And so there is what's called tidal drag. And so the moon is actually kind of behind this tidal force between us. And so what's happening is that it's dragging the moon, it's slowing it down. And instead of it just being slower in orbit, it actually is going to a larger and larger orbit. It's spiraling away from us about 2 centimeters every year. And so precession is caused by the Earth's wobble, which is because the Earth is spinning. The Earth also used to spin faster. Its day, I don't know how long ago, maybe Billy knows this answer, used to be about 12 hours. But you know what I mean? It was, I'm talking millions, billions of years ago. It used to be very short. And so the tidal drag between the moon and the Earth has slowed our rotation down. It has also forced the moon to spiral away from us. There will be a time, and is it 500 million years, that the moon will be far enough that we will no longer have total solar eclipses? Billy, do you remember that number?
I forget. I know that it's something like, I want to say 50 billion before we are both in a tidal lock with one another, but I don't remember how much farther it has to get before we can't have any more total solar eclipses. I'd have to look that up again.
There is a value. It's far, far away from us. But there is a point where the moon will spiral away, and the best we will ever get, as seen from Earth, on the surface of Earth, is an annular eclipse. So I would say, yes, it's going to affect the precession because our speed would be different. But it's not going to be like a major effect, quick. It's not going to be within our lifetime or anything like that. We're talking long-term effects over, eons and billions of years. But it is interesting to learn about that. I remember learning about all that when I was in grad school and trying to hand calculate those effects. This is before computers, folks.
Good times.
Yeah. Any other questions or?
Let's see, I had one other here. You had mentioned before how, even at summer, on the first day of summer at noontime, the sun is not at our zenith.
Right.
Is there a location on the Earth where it would be? And is that related to the tropics that we see on globes and things?
Right. I hope I say this right. So there are tropicals. What are they? Like the Tropic of Capricorn and the Tropic of Cancer on the Earth, and those are latitudes in which, yes, that the sun would be at the zenith. I think I am saying that correctly. And so let me go back to the summer. As you can see, it's really close. East Tennessee is at 36.5 degrees latitude. And so I'm probably sounding stupid here. Is it 23.5?
Mm-hmm. Yeah.
Yeah. Okay. So you'd have to go down a little bit. You'd have to go down to, I guess, is Florida even in there? I think it's close.
It's close. I don't think there's any place in the continental U.S. that you can.
Right. I think it's down below the Keys.
Mm-hmm.
And because I'm from South Florida, I think that was 26 degrees. So yeah, you'd have to go down farther. And right, so that you would see the sun at the zenith, which would mean that your shadow would be directly under you. But yeah, the sun is never at our zenith. Really, like you're saying, for the United States, but especially not for Tennessee, because we have a similar latitude.
Okay, well, thank you very much, Adam. That was a great explanation. So our next presenter, so we're going to go from East Tennessee over to West Tennessee and visit with Dr. Ann Viano, who is with Rhodes College. So Dr. Viano grew up in the San Francisco Bay Area and attended Santa Clara University as an undergraduate. She then received her master's and her PhD in physics from Washington University in St. Louis. and she's been a professor in the physics department at Rhodes College for 22 years. She teaches all levels of physics curriculum, including introductory astronomy, and she is also the manager for the college's observatory. So in her many interests, she is in astronomy, she is interested in astrophotography of deep sky objects and public astronomy outreach. And so she is also currently a board member for the Memphis Astronomical Society, which another one of our speakers is involved with a little bit later on. So I'd like to turn it over to Dr. Viano, and she's going to tell us a little bit more about the motion of the sun. And we may even get to talk a little bit about some archaeoastronomy. So Dr. Viano, please take it away.
Thank you, Billy. I'm going to share my screen here. Hopefully this will work. Okay, I hope you're able to see this now. So as Billy said, I'm from Rhodes College, and here we have a picture of our beautiful college, part of it on the left. And I like this picture because it's taken at sunset. And in Memphis, we have such beautiful sunsets, and I've been given a lot of different reasons about why we have these very vibrant, colorful sunsets. On the right, we have a picture of downtown Memphis looking at a sunset across the Mississippi River. We are right on the Mississippi River. And one reason I've heard for our beautiful sunsets is the rice farming that goes on in Arkansas. They often will burn the rice fields, which puts up some dust, which gives us these beautiful colors for sunset. So I thought we would talk about the position of the sun at sunrise and sunset. That's something that's really easy to observe, and it's kind of a fun project. You can really see a difference over a couple of weeks. And so we're going to talk a little bit about where does the sun rise according to the seasons, which we just heard about from Adam. So here I'm going to show a picture of something that looks a little strange, but let me explain it to you. This is you're a stick figure here, and imagine you're standing out in the middle of a farmer's field, and you have a compass, and that compass would say that this direction is north, this direction is south, and then we have east and west. And then we have what looks like a bowl that's turned upside down, and you're at the center of the bowl. Well, this bowl represents your sky. It's sort of the dome of your local sky. And there are some lines on here. This grayish line, this is the meridian that Adam just talked about that goes from north up through your zenith and down in the south. This blue one that's going from east to west is just an extension of the Earth's equator. It's called the celestial equator. So here you are in the farmer's field, and maybe it's early morning, and you can still see a star in the north. And if you attended our event last month, we talked about this particular star. This is Polaris, and I talked about how the altitude of this star, how high it is above the northern horizon, it's the same as your latitude. So you can always tell your latitude by measuring the number of degrees from the northern horizon up to Polaris. And as Adam mentioned, right now, this is where the North Pole of the Earth points. So this blue line sticking out is supposed to represent the north-south axis of the Earth. And right now it's pointing at Polaris. But as you heard him talk about precession, that's not going to be the case in a couple thousand years. It's going to be a different star. And some thousand years ago, the pole star was actually the star Vega. But right now in our epoch, Polaris is the pole star, and it's kind of a nice landmark for us. However, this isn't the star I really want to talk about today. I want to talk about this star, so the sun. The sun is one of the most observable objects, probably the most observable object in our sky, because when the sun is up, you can't see any other stars. And when the sun is down, then you can observe some other things. So I want to talk about where on the horizon does the sun rise and set. So here I've set this up for the middle of the summer. So this is around June 20th, or the day of the summer solstice. And if you were to go out at about 5:30 in the morning with your compass so you could figure out east and west, you would look towards the east and you'd look for the sun, but you wouldn't find it directly east. You would find that the sun is rising a little bit to the north of the direction east. And over the course of the day, the sun would go up, cross your meridian at noon, and then it would set, and it won't set directly west that day. It will set a little bit to the north of west. And we can move to another season. Here we are in June, in the middle of the summer. Now let's go to winter. We'll go to the winter solstice, which is around December 20th, 21st. And you would do the same experiment. You could go outside early in the morning, say hello to Polaris, and you would wait for sunrise, and you would notice that the sun is not rising directly in the east. It's not rising north of east as it did in the summer. It's now rising south of east. And the sun would rise up, it would cross the meridian, and it would set also south of west. So in the summer, the sun rises in the north part of our sky. It rises north of east and sets to the north of west. But in the winter, it's the opposite. It rises south of the east and goes up and sets south of west. And if you can visualize this in 3D, which is a little bit hard to do, you know, I have a 2D picture here, you might be able to realize that the sun following a path on the dome here is going to be up for fewer hours than the sun over here. You get lots of daylight in the summertime, but in the winter, the sun is very low in the sky and we don't have very many hours of daylight. Now let's look at the point in between, the equinoxes. We're coming up on the vernal equinox, the spring equinox in a week or so, around March 20th. And then we also have the fall equinox in September, around September 20th. On those days, if you would go outside and in the morning time, look for your old friend Polaris, and then look to the east for the sunrise, on those days, on the equinoxes, the sun would rise directly in the east. And on those days, it would follow the celestial equator and it would set directly in the west. So over the course of a year, the sun would go from setting north of west to setting exactly west to setting south of west. And then it would go back to setting exactly in the west and then back to north of west. So this is a really observable phenomenon. And I always know when it's getting close to the summer solstice because my bedroom window faces northeast. And right around the beginning of June, the sun starts moving towards its furthest point in the north and it starts shining on my face right at sunrise. And I always get frustrated because some are times when I like to sleep late when I'm not teaching classes. But then about a month after the solstice, it's no longer shining in my face because it has moved its position along the horizon. So I want to show you some of these observations. So we're going to look at some sunsets and some sunrises. These are images that some of my students took for an astronomy class project. But I asked them to go out and take pictures of the sunset over the course of a couple of weeks. And I've just picked a few images from different students' reports here. So here we have an image and you see a fence, and this is an image at sunset. So here's the sun setting in the west. This green arrow doesn't represent any particular direction. It's just a reference for you. So on the first day of the project, and they did this in the fall semester in the month of September. So on the first day, here was the sun. It's a little bit far, or a little bit to the left of this green arrow. A couple of days later, they observed the sunset again, but now it's much farther to the left of the green arrow. So again, this is just marking this tree. That's a reference. And then a few days after that, one more observation, the sun is way over to the left. So just over the course of a week, you can see that the sun is moving to the left. And if this is sunset and you're looking to the west, to the left of that will be south. So this sun is moving to the south as we are going through the fall season. We're getting close to the equinox. One of these pictures could have been the actual equinox, but the point is that the sun's position along the horizon is further to the south as we're moving into winter, just like we saw in the previous picture. All right, let's look at a sunrise. I had one really ambitious student who decided to observe sunrises, which is pretty rare for a college student, but I think that's fantastic. And so here again, the green arrow is just a reference. It's just pointing at the same tree in each picture. And on the first day of observation, the sunrise was a little bit to the left of this tree that has the green arrow. The next day, now it's moved into the tree a little bit. Then, or a couple days after that, by day 4, the sun is almost in the center of this tree. And then we go a few more days, and now the sun is completely to the right of our reference tree. And then by the last day of observation, it's even further to the right. So as we move into the fall season, and this is sunrise, so we're looking east, so south would be to our right, the sun is moving to the south. Every day it's rising a little bit further towards the south. Okay, a couple more. Here on the top, we have a sunset. So here we have just a reference. The green arrow is just something that's the same in each image. And you can see if you look at the red arrows, that's just showing you where the sun is setting on the horizon. The sun appears to be moving to the left in this image. So here it is, and it's a little bit on the other side of this light pole. Then it's really close to the green arrow. And then by the last observation, it's moved on the other side of our reference light pole. So again, at sunset, we're looking in the west. The sun's position is moving towards the south. I think I might have one or two more. Here we have a reference tree. This is a sunrise again, another ambitious college student. So here's a reference tree, and here's the sunrise on day 1. And then several days later, the sun is much further to the right. So if we're looking towards the east, to the right would be south. So the sun's position is moving towards the south each day. So this is something that's really easy to observe. You can just use your smartphone, take some pictures, try to be at the exact same location every day or every observation, and don't change the scale on your image. And after 6 or 7 images, you will really start to notice the motion of the sun along the horizon. Got a couple more just because I think they're really cool. So here's our reference tree again. I love this one because this person was in the exact same spot for all 6 observations. So here's the reference tree. This is a sunset, and the red arrow marks where the sun is on the horizon. And you can see that it's getting closer to the green arrow as we progress through the days. So again, sunset, you're looking to the west, and the sun is moving left, so it's moving to the south. So it's really a neat thing that you can observe. You can even just sketch it. If you sketch some reference trees or buildings, you can actually sketch where the sun appears to rise or set, and definitely you can notice that change. Now, this kind of observation has been going on for millennia. We are definitely not the first generation to notice this motion of the sun along the horizon. Even as far back as Stonehenge, and even further back than that, people knew that the sun's position was changing over the course of the year. It's changing at noon, it's higher or lower on the meridian, but sunrise and sunset are a really good time to observe the sun because you can actually look at it and not hurt your eyes. And so as far back as 3000 BC, when Stonehenge was just beginning to be constructed, people were observing the motion of the sun, as well as other things. And it is believed, now Stonehenge has a lot of interpreted purposes. Maybe it was a burial site, maybe it was a religious site, but a lot of scientists think that it was a calendar as well. And so at Stonehenge, you have a lot of structures. You have sort of the inner monoliths, and then you have what's called the Sarsen circle. And then you have these outer posts, these aubrey holes. And I don't want to get into all the nitty gritty, but I just want to show you that if we line up the cardinal directions, north, south, east, and west, there are some alignments with the sun, the position of the sun on the horizon on certain days of the year. If you're at the center of the circle, then the summer solstice, the sunrise lines up with the heel stones here. So if you're standing right at the center of the circle, you would look in a certain direction, and if the sun lines up, then you know we're in the middle of the summer period, astronomical summer. That's the longest day of the year, and that you're going to be heading into harvesting season and then into winter. And there are also other alignments here The sunset in the summer lines up with one of the monoliths. The sunrise on the winter solstice also lines up with one of these inner monoliths, and then the sunset in the winter as well. But most scientists who have studied this in depth also think that Stonehenge was a moon calendar. And that's a much more difficult observation. The sun is pretty easy to observe. The moon it's easy to see, but to actually figure out the moon cycles is a little bit trickier. And I know this is really tiny and hard to see, but this is just an overhead picture of Stonehenge. So here are the monoliths in the center and the Sarsen circle. And then there are lots of holes out here, but there are these 4 posts here called station stones. And it turns out that if you're at a certain station stone, you have some sun alignment. So here's the summer solstice sunrise. If you're standing at station stone 93, you could look towards 94 and you would have a nice direct lineup for sunrise on the summer solstice. But you also have moon sets and moonrise alignments among these station stones. So some of the latest thinking is that the first part of Stonehenge were these Aubrey holes where there may have been posts, and it was a moon calendar. And the archaeologists now think that these inner stones, the big stones that we think of when we think about Stonehenge, were actually added later. So maybe it was a moon calendar first, and then it became a solar calendar. Pretty hard to know the actual purpose of some of these things. Now, the Britons on the Isle of Britain were not the only ones to make these kinds of solar calendars. Right here in Mississippi, we had the Mississippian Indians, who were a mound builder type of Indian. And being in Memphis, most of us in West Tennessee have learned about these because they were up and down the Mississippi Valley. Here in Memphis, we have the Chucalissa Indian Mounds, which is a nice site to visit. But I wanted to talk about one that is up in Western Illinois, Cahokia Mounds. Cahokia Mounds is right across from St. Louis, Missouri. And the peak of this civilization was around 1100 AD. The city itself was about 6 square miles, which is a pretty good sized city for that time, a population of about 20,000. And in the site, there are these earthen mounds that are built that are not uncommon to ancient civilizations. You see them in South America and Central America as well. And then in Egypt, you have the pyramids. So this is not an uncommon type of structure to be seen in the ancient world. But what's interesting about Cahokia is that they unearthed a circle where they believe there were wooden posts erected in a nice circle. And there was some alignment with some of the larger mounds at Cahokia. So they have named this circle of wooden posts Woodhenge, which is kind of a funny name, but it reminds us that it was probably some kind of solar calendar. And in this case, it had 48 cedar posts, and there were alignments with sunrise and sunset positions on the solstices. And one of the mounds, the largest mound called Monk's Mound, was actually aligned with sunrise on the summer solstice. So if you were at the center of Woodhenge and you looked for the summer sunrise on the summer solstice, it would be near one of these posts, and it was also right at the edge of the largest mound for this community. There were also alignments with other mounds. This is the sunset on the summer solstice, and there was a mound aligned with that position on the Woodhenge circle. So it's really interesting that these ancient peoples were able to make these observations and make conclusions about the cycles of the sun and maybe the moon as well, and construct these calendars. I believe they probably used this to tell when it was time to plant, or when it was time to get ready to harvest, or when it was getting close to winter and you needed to, get supplies to get through the winter. If we go across the country to New Mexico, there's a very rich history there with the Anasazi Indians. And the one I want to talk about has to do with the observation of the sun again. This is the sun dagger at Chaco Canyon in New Mexico. And if you're hiking around, it doesn't look like much. You come upon a site where there are these 3 large stones. These are taller than a human. I don't have a picture of someone to scale, but These are much taller than a human being. They're 3 large rocks that you couldn't move even if you tried. And it doesn't look like much, but if you were to walk around, see that up on the rock, there is a spiral that has been carved into the rock. And it is believed that this was used to mark the position of the sun at different times of the year. And in this case, the sun was shining through the slits made by these 3 big rocks. And if you were to be there on the winter solstice, the sun would shine through those slits in the rocks, and you would get 2 daggers on either side of the spiral that's been carved into the rock. In the summer, you get 1 dagger that pierces right through the center of the spiral. So it's kind of cool. Here are actual pictures of the sun dagger on that day. So this is the winter solstice, where you have 2 daggers that bracket the spiral. And then on the summer solstice, the dagger pierces right through that spiral. So I think they probably started on the summer solstice and put a mark, and then just kept carving that spiral until they reached the winter solstice, and then they knew exactly how big to make that spiral. So they could then mark winter and summer to help them plan, again, their calendar. So in summary, I just wanted to say that the ancients used all types of observations as calendars. So we've talked about using the sun and maybe the moon to set your calendar. People use daily motion of the sun and the stars as well. People use phases of the moon. Some cultures use the positions of the planets to construct a calendar, although that's very, very complicated, and yet some cultures did figure this out. The ancient Babylonians did an amazing thing by figuring out an 18-year cycle of lunar eclipses. That's very complicated, very difficult to figure out. But this is a Babylonian tablet from 464 BC, where it actually records observations of eclipses. And this 18-year cycle is called the Saros cycle, and it's what they use to create their calendar. The Mayan calendar is also based on the Saros cycle, which is a very complicated cycle, and how they were able to figure that out based on observation, naked eye observations alone, just amazes me. Some cultures even recorded major events that happened in the sky, and particularly supernova. This is, again, at Chaco Canyon, the Anasazi have a pictograph where there's a crescent moon, and there's a bright star next to it. And the handprint is thought to either mark the site as a sacred site, or maybe it's just the painter's autograph. But this was drawn in 1054 AD. And we are going to hear about a supernova that exploded in 1054 AD in a little bit from a few other panelists. And we are pretty sure that that is the event that is recorded here. It was recorded in 1050 AD or so. This is when this is dated to. So it seems like there's a correlation between this pictograph and this major supernova. This particular supernova would have been bright enough to see in the daytime. So it would have been a very noticeable event, and it's not surprising that people would have recorded this. It's not recorded in European history because this was the Dark Ages and people weren't writing or anything until the Renaissance came around, but we do have records of it in different cultures. So that's what I wanted to talk about tonight. If there are any questions, I'm happy to take them.
All right, well, thank you very much, Anne. That was really incredible. Learned a lot there. One of our viewers said that the experiment that you do with your students really helps to make Stonehenge come to life. So kudos to doing those kinds of projects. Let's see, there were a couple of questions. Actually, so does the tilt, if the tilt of the Earth was different, so if it was tilted more or less, would we see a change in how much the sun moves over the course of the year along the horizon, or would it basically be the same?
We would definitely see a difference. So the motion along the horizon is roughly 23.5 degrees on either side of east or west. So if we were tipped at like 50 degrees or something much larger, the position of the sun would change much more drastically over the course of the year.
Okay, so I guess a planet like Uranus, which is basically on its side, it would see it go from south to north over the course of its orbit.
Yes.
Wow, that'd be something pretty interesting to see. Does the rate at which the sun appears to move along the horizon change over the course of the year?
It does. If you make this observation, it will appear that as you get closer to the solstice or the extremes of its motion, it changes more quickly at those times. And then the change from day to day slows down as you get towards the equinox. And my students actually commented on that, how, you know, as they got farther into their observation, it seemed that it was changing more every day than it was right around they were doing this around the autumnal equinox. And so they were just using a smartphone app where you can measure the azimuth, and they would just kind of point it at the sunset and try to get a reading of the azimuth. And they noticed that it was changing at different amounts, which is kind of interesting. Good question.
All righty. I don't think we have any others at the moment, but thank you very much. And let's see, our next presenter is Theo Wellington. Well, let me first start by saying, if you haven't gotten your toilet paper, you need to have your toilet paper for our next presenter, okay? So make sure you get your toilet paper, about 6 feet long at least, and then a pen or a marker. So Theo Wellington is all the way up in Goodlettsville, so in the north, just north of Nashville. And she's a member of the Barnard Seaford Astronomical Society. She's also a JPL Solar System Ambassador. And if you've been to the Adventure Science Center, then you've probably seen her around there as well. So, but we're going to turn it over to Theo, and she's going to do a fun hands-on project with some toilet paper. So Theo, what are we going to do with that?
All right. So, yeah. All right. Well, I'm just going to Z in and out of space here. So we've kind of been looking at how things look to our eyes here on Earth. We're going to step out now and do a little bit of scaling in our solar system, because it's hard sometimes to wrap our heads around how far away things actually are. So textbook illustrations are really no help, and that's what I've used for my kind of funky background here tonight, because this is what you see in every single textbook. Let me move over a bit here. The planets are all bunched up together. They're not the right size. They're not the right distance. And so we get a really wrong idea in our heads about how this all works. And sometimes we have scale models. I have a really cute scale Earth. Let me get this right. And a scale moon. There we go. They're correctly sized relative to each other, but to get them the right space apart for this size, the moon's got to be 50 inches away. That's hard to do with just your arms. But I assure you that if you do, the cool thing about this particular size is that that moon, if you hold it up to the sky, is really close to what the actual moon size is in the sky. So it works very well as a scale. And you might think that's too small, but it's not. I promise you, you can cover the moon up with your pinky finger any night. I don't care if it's a supermoon or what. But it gets really hard to know the distances between anything else, because other stuff, like there's my Earth, here is Mars. They're correctly scaled, but Mars at this scale is 2 football fields away, and that's when it's closest to us. So clearly, this doesn't help us any to get the whole solar system kind of in our heads. So if you've been hoarding this until now, hopefully now we can stop hoarding toilet paper. So instead, like Billy said, get yourself a length. 6 feet works if you're smaller, if you're a short person, or 6 years old or something. Make it as long as you are tall. This is a very personal scale model. So on this scale, first thing we're going to do is we're going to take one end and we're going to make it the sun. Okay? And almost anybody can do a better job than I can. So you're welcome to decorate it, use markers. If you're old school and you have some of this around the house, this is adding machine tape. It works really well. It's a little bit easier to draw on than toilet paper. But since we hoarded all this, we're going to use toilet paper tonight. So we have the sun at one end of what's going to be our solar system. And then on the other end, let's see if I can get this right so I don't put them on opposite sides of the paper. Here we go. The other end, and I'm not artistic, so here's my solution. The other end, that's a nice, let's see if I can get this to the camera, is going to be Pluto. Because we still love Pluto, right? Pluto's a really nice planet. It's going to stand in for all the stuff that's out there past Neptune. So it's still part of our solar system, and we love Pluto. So that's the other end of our scale model. Also, it makes the scale work better. All right. First thing we're going to do is you're going to take Pluto and the sun, bring them together. So you're folding this toilet paper in half. Make a nice little crease here halfway through. Then take your marker and make a line right there. That's halfway, okay? Halfway between the sun and Pluto. There we go. What planet do you think is halfway between the sun and Pluto? I'm going to tell it to you in a way that you're never ever going to forget it. If you take your folded in half length of toilet paper, hang it down behind your back. This is a terrible middle school joke, but that's okay. Where the paper ends on your body is your clue to what planet comes halfway between the sun and Pluto. Yep, it's the seventh planet, Uranus. And we do say it like that because otherwise there are so many jokes. We know most of them after being in the planetarium for a long time, but it's beneath us to tell them. But everybody tells them to us. So, all right, so there we've got our handy Uranus. All right. Now, the interesting thing about Uranus is that there's actually a local story with this. And I'm going to see if I can share my screen for just a minute. All right. See if that shares properly. Share. Technology, it's always fun. All right. Hopefully you guys are looking at a picture of the United States. And there are 3 dots. So in 2009, a student by the name of Jacob Larson came to the planetarium with a proposal. He wanted to make a really huge scale model of the solar system from his home planetarium in Bay City, Michigan. That was going to be Pluto, and then he was putting the sun at Cape Canaveral, and he was looking for planetariums at the correct distance to be the planets. Now, if you look at the map, what you notice is that it's about halfway where Nashville is between Florida there and the Delta College in Bay City, Michigan. And so right away we knew, oh my gosh, we're being asked to be the planet Uranus. And that was what we proudly became on that scale model. So on the drum of the planetarium is a plaque that commemorates this National Solar System Project. We are Uranus. So that's just kind of a fun side story there. And today, on this date in history, 240 years ago, Uranus was discovered by astronomer Sir William Herschel in his backyard observatory in Bath, England. So that's kind of fun. So anyway, you will never now forget that Uranus is halfway across the solar system. But now we need to fill in a few more planets. So we're going to take our scale here, Uranus in the middle. All right, we're going to take that and we're going to fold it again. So now we're going to end up with 2 creases, okay? So one is the other in between Uranus and Pluto. So what planet is in between Uranus and Pluto? Anybody want to take a guess at that? And yeah, it's that other outer gas giant, my buddy Neptune. So we're going to put Neptune on our scale model there. And I hope that all of you out there are much more artistic than I am and can have a little bit of fun decorating up your scale models. All right. Then we're going to have another fold that comes between Uranus and the sun. I'll have to redo that right there. What planet is on the other side? What planet is halfway back to the sun from Uranus? I'll give you a hint. It's the planet with the absolutely stupendous rings. Yeah, it's our buddy Saturn. So Now we've got quite a few planets lined up. So we're going to put Saturn on our list. So we're getting to have quite a nice little lineup here. Of course, I've got some people on the wrong side now, but that's okay. So we need to add a few more planets. So we're going to take our tape. We folded it in half once. We folded it twice. Now we're going to fold it one more time. And this time we're only going to pay attention to the fold that's between Saturn and the Sun. So what planet comes between Saturn and the Sun? And it's the other big planet, right? Jupiter. Let's see if we can get Jupiter on our model here, right about in that center. Now, as you can see, we're actually getting kind of close to the Sun, and we still have a few more planets to go, but that's okay. So here we go. So if you want to now, you can just start at Jupiter, and we're going to fold it in half again. Take this guy off. Okay. Fold it in half just up to Jupiter. This is where it gets a little tricky. What's halfway between Jupiter and the Sun? Well, you know, astronomers actually noticed that there was this almost really regular spacing going on, and so they thought there should be a planet there. I mean, there are these regular spacings. Now, before we had telescopes, we didn't see anything, but when we got telescopes, we started looking, and we actually did find something in that space. So it was a planet. Then we found another thing in that space. Okay, 2 planets, yay. And then we found more and more and more until we suddenly realized that we weren't looking at a few planets. We were looking at thousands and thousands of tiny little bits of rock. The asteroid belt is what's kind of halfway between the Sun and Jupiter. So you can draw some tiny little dots in there. Ceres and Vesta are the 2 big guys, but they're all small. Turns out Jupiter, being the big guy on the block, Jupiter's gravity simply will not permit the formation of a planet at that place. So there's just little things that are leftover bits of the solar system's formation. Sometimes they fall down, and we have, like this past week, a rock came down and part of it splatted on a driveway in England. That was pretty fun. Well, sometimes space comes to us. So now we're going to do yet one more fold. Now we're down to a really small bit of fold. And so the next fold is still a little tricky because the planet that we're going to put there is the Earth. That's about halfway between the asteroid belt and the Sun. So now you're saying, wait a minute, you missed somebody. And you're right, I did. Poor little Mars is kind of in an oddball place. So it's about halfway between the Earth and the asteroid belt. So you can put Mars in. Mars is the only planet currently inhabited only by robots, except for maybe, microbial life. We could get lucky and find some. But we've been invading it for some years now, and we just sent another spacecraft to land on the surface. All right, so we're almost done. We don't actually need to do any more folds. Between the Sun and Earth, all you need to do is split that distance by about 1/3. So that ends up looking like, this has got the answers on it. Hang on a second. There we go. Let's see if I can get that in the camera view and have it look like something. So the Sun's at the bottom. There's the Earth. So you put 2 lines that are each about 1/3 of the way in. The first one, closest to Earth, is the planet that's known for being so beautiful in the night sky. It was named after the goddess of love and beauty, and that's our buddy Venus. Here we see her without her lovely shroud of clouds. It's an interesting, mostly volcanic place when it's like that. Okay, and then last but not least, the planet that moves really, really fast. So it was named for the speedy messenger of the gods, Mercury. So cool. now you've got a huge, long, scrolling, wee model of the solar system that is every bit as long as you are tall. It's your own personal scale model. So that's pretty cool. Now, that's our solar system, our group of planets. What about other planets that we see going around other stars? Turns out that there was a star system named Kepler 90 where we found 8 planets. Well, that's kind of familiar, right? We have 8 major planets. There's 8 planets. How would that scale in that system? Okay, it's a small star, so they're closer in, but they're really closer in. All 8 of those planets would fit between Earth and the sun. So it's just a little stubby piece of paper for that solar system. So planets come in all different sizes. They come in all different spacings, depending on, what the size of the planets that were there were, what kind of things formed. It's just really interesting. We kind of thought all solar systems would end up looking like ours, and they don't. They're very different. So it's amazing how much complexity out of simple stuff you can get. But hopefully you enjoyed making your own solar system. And if that was a little bit quick, you can always rewind later on. It's a fun project to do. And like I said, you guys are much better artists than I am. Please decorate them. And if it's really pretty, send it to Billy at Dyer, to info@BSAS, and we'll enjoy looking at your lovely scale model of the solar system. All right. So I'm going to pass it back to Billy.
All right, well, thank you.
Or ask if there are
That was
yes.
a fun project. I'd never done a personal solar system, so thank you for that. There were 2 questions that came to mind. So when you were mentioning the asteroid belt, in Star Wars, when the Millennium Falcon is going through that asteroid field, is that basically what we would see if we were in the asteroid belt? Or let's say we were standing on asteroid Ceres, would we be pelted by all these other asteroids, or what would we likely see?
We'd be looking around at pretty much nothing. I forget what the average spacing is, but because they're small and you're not going to see them anyway, space is really big. And we have sent spacecraft flat through the asteroid belt several times, and you just don't hit anything. They are incredibly spaced apart. You can just sail right through there. So yeah, you are actually not doing this little duck and dodge thing. You are just sailing straight through. The only way you find an asteroid is if you mean to be there. And we've done that too, but generally speaking, it's amazing. Space is just so huge. And it gets worse. There are several thousand known objects out with the Pluto group, and they're super far apart. So it's just, space is really empty space.
All right. And I think you may have touched on this a little bit, but we were talking about how far the planets are from the sun, and the farther you get, the bigger their orbits are. So it makes sense it would take them longer to go around. But is that the only factor that contributes to how long it takes them to go around? Is it the size of their orbit or something else?
It's pretty much just how far you are. And in fact, there is a cute little relationship between how far you are and how long it takes you to go around. And those 2 things alone determine the orbit as far as its size. It's kind of, a lot of times we use that bent sheet model where, the sun weighs down the middle of the sheet, and then you put an object in orbit and it's going on the sheet. And where it is, it's going to have, if it had any other speed than what's going to keep it going at that distance, it would fall inward. And so every planet has its own speed for that particular distance. And I meant to share, hang on just a second here. Astronomers don't like to memorize, a lot of numbers either, because it's just too much to carry in your head. So, we cheated a little bit on the scale, because at 6 feet of tape, it doesn't matter, right? You can't really get blindingly accurate. But we like to call the distance from the sun to the earth 1 AU. That's easy. You can remember 1. So then you only have to remember that Jupiter is about 5. And Saturn's not quite twice that, but 9, and so on. So we call that the astronomical unit. And we actually used that before we knew the actual distances, because it turns out that all you need, if you know how long it takes to go around, you know how far out it is. That's one of Kepler's laws. And so it was not until really the late 1700s and maybe even the 1800s that we had a decent idea of what 1AU actually was. And that's a whole other interesting story, the transit of Venus observations. So yeah, it's really just where you are. You're going to be going a certain speed to be in a stable orbit, and you're going to go around at that in that time. That's kind of fun.
So as we get farther out in the solar system, are the planets speeding up or slowing down?
Ooh, I need to find out what the exact. I mean, it's a huge orbit. I think I want to say you're still slowing down, but I don't know. I'd have to figure out what the orbital speed is. I mean, Pluto's got 39 astronomical units. So everybody remember, it's almost pi day, right? So the circumference of a circle is pi d, right? So 80 astronomical unit d, it's a long way around, 3 times that. So, and you're going to go around in, hundreds of years. I should look that up, what the speed is. But I want to say it's slower in any case. So it's you can calculate it. That's a good for the student thing to do, especially with Pi Day here.
Yeah, that's a good way to end a Saturday night. Sit down, do some calculations, right? That's my idea of a fun Saturday.
One of the things I like about astronomy is a lot of things you can do, like back of the envelope, because you don't have to be exact. So you can just round everything off and reckon it, in things that you can not even use a calculator for, and get an idea in your head for these things. And I think when you do that, then it makes it easy, because then you kind of have an idea in your head. You didn't just memorize a number. And so that's kind of a fun thing to do. And I like astronomy for that. That's a lot of astronomers work that way. If you ask them a question, they'll just round everything off, because all those extra digits, don't mean anything to you viscerally. And so you just say, okay, about this, and it'll be close. So, and the same thing is true on the smaller scale with our satellites as well. And it's kind of non-intuitive that you kind of have to slow down, but you have to be out there to get to a particular orbit. And so you have the guys that are out there at 36,000 miles or so, whatever geosynchronous orbit is, and they go around once a day so that they always hang over the same point. And then you have your GPS satellites that are whipping around way, way under that, just a few, 100 miles above our heads. And they do stay in orbit, but not forever. So it's kind of fun to be able to look at things and to reckon it yourself, but scaling it in a way that is using small numbers, easily remembered, is a good way to do it. So I think for the Earth, I want to say we go around the sun at 66,000 miles an hour, something like that. So if people want to take a look at what Venus or Mercury do, that would be a fun exercise.
There was a question. So the mass of a planet has no impact on its velocity around the sun. Is that correct?
That is actually kind of fun. That's also not intuitive. But yeah, the way the math works out, the mass ends up canceling out. And the thing that really matters is the mass of that great big thing that sits at the middle of the solar system. And we're just so much, in your physics textbook, they would call it a test mass, right? Yeah, it's inconsequential almost. The only two things that matter in the solar system are the sun and Jupiter. Jupiter is more massive than everybody else. And that said, we don't notice tides from Jupiter, right? We don't notice any gravitational effects at all from the other planets. Sorry, astrology. Let me unshare that screen there. So the moon, as small as it is the only thing that really pulls on the Earth. And like Adam was saying, it has some many and varied effects. If you've been to the beach, you've seen the tide move the water in and out. but the Earth itself moves under your feet twice a day as well. And I'm waiting for the day when our cell phones are good enough with position to be able to actually see that, because that would be kind of cool. It's just that rock is harder to move than water. And we in turn exert a tide on the moon. And so we don't think about that because, you know, if we don't live on the coast, we don't worry about tides, and we can't really see the Earth moving under our feet, so we don't think about that. But the moon is our buddy as far as gravity, and everything else is just along for the ride. We can just watch it.
All right. Well, thank you very much, Theo. Okay, so now we're going to head back over to Memphis, and we're going to visit with Jeremy Villman, who is with the Memphis Astronomical Society. And Dr. Viano had alluded to a supernova that was observed in the year 1054. So we're going to hear a little bit more about that. So Jeremy, let me turn it over to you.
Thanks a lot, Billy. Quick sound check. Give me the thumbs up. All right. Well, it's been a great program so far tonight. And I'm going to talk about one of the most mysterious and exciting objects in the universe. So let me go ahead and share my screen here a second. So again, we're clouded out tonight. I'm going to show some footage at the end of this of the Crab Nebula through my telescope to kind of wrap it up here. But tonight's object is the Crab Nebula, or Messier object number 1. And it's actually located in the constellation of Taurus the Bull off of the left horn. And if you're familiar with the night sky this time of year, Orion is a very familiar constellation. Orion holds up a shield to guard against Taurus the Bull. So it's to the right of, if you're looking at Orion, this constellation would be to the upper right. And the Crab Nebula M1 is located off of the left horn, also off of the Aldebaran side. So the bright orange giant star Aldebaran is pretty recognizable, and that's where you find M1. Not the easiest of the Messiers to find. There's a little bit of guesswork to finding it, but it's still pretty easy to find with a telescope, even if you don't have a go-to controller. It's a supernova remnant. Again, we talked about this earlier. About 1,000 years ago, the Chinese recognized a guest star. Imagine a star visible 24 hours a day, including in broad daylight, high noon, clear blue sky that could still be seen. Some accounts have it as bright as a first quarter moon. So very interesting. This is one of the reasons why we're all craving the opportunity possibly to see this in our lifetime. Constellation Taurus, it was visible 1,000 years ago. Today it's at magnitude plus 8.4, which means you need a telescope to find it because it's too dim. And it's about 6,500 light years away. This is the first entry into Charles Messier's catalog, and to the best of my knowledge, somebody correct me on this, the only supernova remnant in the Messier catalog. And this is really the one that kicked off Charles Messier's quest to build this. He lived around the time of George Washington. In 1758, he was looking for Halley's Comet and accidentally stumbled across this, didn't know what it was, mistook it for Halley's Comet. Recognized his mistake later, and so decided to build out a catalog of all the things that weren't comets. And the fact that he came up with 110 of them, I guess, kind of makes Charles Messier the poster child, if you will, for astronomical ineptitude. But anyway, this is invaluable for backyard astronomy because going through the Messier catalog is really what helps you learn the night sky. So on July the 4th, we've seen some amazing fireworks. Nothing compared to what the Chinese saw in the year 1054. They recognized a guest star. We believe that the Crab Nebula supernova remnant is the result of this supernova because of accounts that we found from the highlighted passage here. So tying those two together and the position in the sky is kind of the smoking gun, if you will, for an exploding star. And Anne alluded to this earlier. This drawing that the Anasazi drew in New Mexico about 1,000 years ago also seems to coincide with the discovery of this guest star. And turns out on July the 5th, 1054, the moon was a crescent moon and located very close to this very bright star. So there's reason to believe that this depiction here in the Chaco Canyon in New Mexico is in fact the supernova. And of course, the hand, we're not exactly sure whether it has some type of metaphysical significance, whether it's the artist's signature, or whether it's just the artist saying, hey, you, talk to the hand. We're not exactly sure. So there are two types of supernovas to kind of simplify this. They're both, supernovas are exploding stars. So the type 1A occurs when a dense nugget called a white dwarf, which is a stellar remnant. Our sun will become a white dwarf when it dies out billions of years from now. If it's in a binary system and the gravity accretes matter from a nearby companion, that can cause it to explode. That's a type 1A. We're not going to talk about that tonight. That's a very important type of supernova, but we'll save that for another time. Then there's what's called a type 2 supernova, and that's the core collapse of a massive star. When a star basically implodes on itself, rebounds, and then explodes. So that is a type 2 supernova, and the star that caused the Crab Nebula was a type 2 core collapse supernova. Now, to kind of set this up, a little brief summary here of stellar evolution. So on the left is the Hertzsprung-Russell diagram, and this is the screwdriver in the astronomer's toolkit. And the Hertzsprung-Russell diagram basically graphs all the stars that we see based on their mass and their luminosity and their temperature. So on the left side here, let me actually get a better pointer. On the left side here would be the luminosity of the star, and then that's the y-axis, and then the x-axis is the temperature. And we've covered spectra and the different classes of stars in previous star parties, the O, B, A, F, G, K, M, N significance. Well, that's the x-axis here. So your O and B stars are your hot blue and very, very luminous stars, and then your M stars are the cool red stars here. Now, for the purposes of tonight, there's a band of stars in the middle here called the main sequence. 85% of all the stars in the universe, including our sun, by the way, are what are called main sequence stars. To be a main sequence star, you have to fulfill 3 criteria. Number 1, in the core of the star, your energy source is converting hydrogen into helium via nuclear fusion processes. So your nuclear fuel in the core of the star, of a main sequence star, is hydrogen to helium. So that's criteria number 1. Number 2, the star has to be in what's called hydrostatic equilibrium. And basically what that means is that the radiation pressure that wants to blow the star to smithereens is balanced by gravity. You can think of stars as giant hydrogen bombs. If you've ever seen a hydrogen bomb explode, it's just a chilling sight. That's essentially what stars do. But the reason why they don't blow themselves to pieces is because gravity wants to crush the star down to a singularity. Those two forces balance, and you have a state called hydrostatic equilibrium. So that's criteria number 2. Number 3, the star has to be in what's called thermal equilibrium. And that means that the energy generated in the core of the star has to balance the energy that's being transported off of the surface of the star, and we call that luminosity. So luminosity is shining. So it's shining energy away, and the energy that the sun or that the star is shining has to equal the energy that's being generated in the core, and we call that thermal equilibrium. So these are the 3 criteria for a main sequence star. Now let's talk for a second about luminosity. The luminosity of a star is its power output. And of course, it's how bright the star is. We say the sun is shining. So an ordinary person would say, the sun is shining today. A person who nerds out on astronomy would say, the sun is losing energy today. It's leaking energy out of the photosphere of its star and radiating it into the cold blackness of outer space because the sun is hot and dense, and hot, dense objects radiate into cooler areas because nature abhors a vacuum, and that's just how it works. So a sun like a star like our sun, when it's shining, it's literally losing energy. It's leaking energy out of the surface of the star. The reason why it doesn't burn out and fade away is because nuclear fusion in the core makes up for the energy loss at the surface, and that's why the sun can shine for 10 billion years. Now, luminosity scales with the mass of the star. So the more massive the star, the more luminous it is, and consequently, the more rapidly it's losing energy out of its surface. That's why massive stars, the more massive a star is, the more quickly it burns out. And you can actually calculate the main sequence lifetime of a star. It scales like 1 over m cubed. And in this case, mass, the mass of the star is in solar masses. And you just multiply that by 10 to the 10, which is 10 billion, and 10 billion is the sun's main sequence lifetime. The sun will be a main sequence star for 10 billion years. So for example, let's take a star like Betelgeuse. Again, this is the red supergiant star in the upper left shoulder of Orion. It's about 15 solar masses. So doing this quick calculation, if you cube 15 and divide it into 10 to the 10, you come up with a number of about 3 million. So Betelgeuse, even though it has 15 times more mass than the sun, it will only be a main sequence star for 3 million years. In fact, it no longer is a main sequence star. So we say that the main sequence is a mass sequence. The more massive the star, the more luminous, and the more quickly it moves off of main sequence into the latter stages of evolution. So for the purposes of tonight, let's talk about high mass stars. And again, a high mass star is a star that's 8 solar masses or greater. This is where all the excitement happens. I'm going to kind of briefly walk you through this here. You can see here we've got successive energy tapping sources. These are successive nuclear fusion sources, if you will, in the star's attempt to generate energy in the core to prevent gravity from crushing it. Stars are in this tug of war between gravity that wants to crush it and radiation pressure. So the star needs to keep tapping into successive nuclear fusion sources to prevent gravity from winning. So in a massive star, we start with hydrogen to helium burning. And again, for the sun, it'll be 10 billion years, but for a high mass star, it's only about 10 million years that it's going to burn hydrogen into helium. So while this happens, the hydrogen in the core is converted into helium, and the helium sinks into the core of the star like an ash. Think of a wood burning fireplace. You put giant logs in there, you let them burn for a while, the ash is going to accumulate in the center. And when the hydrogen fuel gets basically exhausted, the helium will collect in the center and shoulder the hydrogen burning out into a shell around the core. So the helium accumulates in the center. We've now got a hydrogen burning shell around the helium core. Gravity starts to compress the helium core. When that happens, it heats up. And when we get to 100 million degrees Kelvin, helium burning will kick in. And now I've got helium burning and a hydrogen burning shell around it. Helium in the core, hydrogen burning shell around it. At this point, the star is making more energy than it can radiate away. That excess energy turns into work, and the star swells up into a red supergiant star. And in this case, it can be as large as the orbit of Jupiter, 5 astronomical units. Now, the helium burning will go for about 1 million years, and the products of that are carbon and oxygen. So you have this carbon-oxygen core, and then eventually that accumulates toward the end of the helium burning process. Helium gets shouldered out into a shell. I've still got a hydrogen shell, and then this carbon-oxygen core will collapse under its own weight. Now, if it was a low-mass star like our sun, this is where it would get off. So basically, the core and the envelope would separate, planetary nebula phase forms, and then the carbon-oxygen core would compress into a white dwarf, and the game is over. But for high-mass stars, we can actually get hot enough to ignite the next level of fusion, which in this case is carbon burning. So carbon and oxygen, when they reach 600 million Kelvin, begin to fuse into heavier elements like neon, magnesium, aluminum, etc. And this goes on for about 1,000 years. Again, once we get past the helium burning stages, the nuclear fusion stages of the star speed up pretty rapidly because I'm getting into the fusion of heavier atomic nuclei, and they're less efficient processes. In fact, when I get down to neon burning, you can see the temperature and the core densities are just astronomically high compared to where we were in the main sequence phase. So at about 1 billion degrees Kelvin, neon will start fusing to form oxygen and magnesium. I've now got a core density of 10 million grams per cubic centimeter. It will last for a very short period of time. The other problem that starts to happen, so at this point in time, the star is getting desperate. It's trying to tap energy sources to prevent the gravity from crushing it down, and it's having a harder and harder time doing this. Neon burning is very inefficient. In fact, at this point, the star is leaking so many neutrinos that it essentially shines the neutrino luminosity, if you will, is greater than the photon luminosity of the star. And it gets really bad when we get into oxygen burning, which lasts for a much shorter period of time even yet than that. Finally, we get down to silicon burning, and that lasts for only a couple of days. At this point, I fused elements heavy enough where I can literally burn one solar mass of silicon in only a couple of days, and that results in a nickel and iron core. So the picture of a high mass star looks like this at the end of all of its nuclear fusion burning stages: an iron core, a silicon shell, and then all these other shells: silicon, oxygen, neon, carbon, helium, and hydrogen, all still burning, but I'm left now with an inert iron nickel core. And the energy, the efficiency of the later stages of burning, of fusion, if you will, are very inefficient. To draw stars as cars analogy, it would be like, you know, putting high octane jet fuel in your car for main sequence hydrogen to helium burning versus water diluted kerosene for oxygen burning. So the star is in a lot of trouble, and essentially it's about to be doomed. So now we get to iron in the core. What happens? Iron is what we call the nuclear impasse. At this point, we can no longer fuse iron to get energy out through nuclear fusion. And the reason, because atoms with atomic nuclei heavier than iron actually require energy to build. So if I wanted to go from iron to tellurium, for example, one tellurium nucleus is actually heavier than 2 iron nuclei. So I need energy to make heavier elements. And of course, the star doesn't have that. So all of these nuclear processes to get from hydrogen to helium would actually generate energy. So in the case of hydrogen to helium, 1 helium nuclei is lighter than 2 hydrogen nuclei, and the difference in the mass is converted to energy, B equals E equals MC squared. Well, I'm not able to do that when I get past iron. So we say that this is an energy sucking process, and it really sucks for the star because now it's doomed. So let's talk about the iron core collapse. We've got this iron core now compressing under the force of gravity. It's about 1.2 to 1.4 solar masses. When the temperature exceeds 10 billion Kelvin and the density exceeds 10 billion grams per cubic centimeter, again, that's 10 billion times denser than water, 2 energy consuming processes kick in: photodisintegration and neutronization. Photodisintegration is when high energy photons like gamma rays essentially melt matter. So all of these heavy elements that the star has spent millions of years building through nuclear fusion in seconds melt away back to their constituent components: helium, neutrons, and protons. And the significance of that I'll point out in just a second. So you're reversing the fusion process in seconds. The second thing that happens is neutronization. The gravity is compressing protons and electrons to form neutrons. And in the process, it releases a tremendous amount of neutrinos. So neutrinos are just pouring out of the core of the star, and that takes away even more energy. So at this point, the star is doomed. Anything it tries to do to generate energy, it can't do it anymore. And you've got these 2 processes that are literally robbing the core of energy, and that hastens the collapse due to gravity. The iron core collapses and bounces. Now let's walk through this process. At the start of the process, the diameter of the iron core is about the size of the Earth, 6,000 kilometers. 1 second later, it compresses to about 50 kilometers, which is the diameter roughly of Davidson County, where Nashville is located. Also, the density ramps up by 6 orders of magnitude, from 10 to the 8 grams per cubic centimeter to 10 to the 14 grams per cubic centimeter. And the edge of that collapsing iron core is falling in at about 1/4 of the speed of light. When that happens, a third force comes into play that normally only is in play with atomic nuclei. But the density of this matter is now on the order of the density of atomic nuclei. And that third force is the strong nuclear force. And it's a curious force because it can be both attractive and repulsive. So in comes this collapsing iron core at 1/4 of the speed of light, gets to the density of an atomic nuclei, strong nuclear force ramps up, stops it, it rebounds, overshoots, and springs back. And that creates a shock wave that rams into all of this material falling into the core of the star. Now, to put this in perspective, the total kinetic energy of the shock wave that bounces from the core into the surrounding gas falling in is 10 to the 51 ergs. That's more energy than our sun will put out in its entire 10 billion year lifetime. Also, there's a neutrino burst equivalent to 10 to the 46 joules of energy. Neutrinos are just pouring out of the star. Now, you know, you've heard stories about supernova, and if our sun was to go off, you would need something like 2 billion SPF sunblock to guard you from the flash of the supernova. Well, even if you had that sunblock, that's not what would kill you. The neutrino flux would kill you before the flash did. What is a neutrino? It's a particle that is very small, only 1,000 times smaller than an electron. Billions of neutrinos are streaming through your body right now from the core of the sun and other stars throughout our galaxy. And yet they're so weakly interacting that even though neutrinos are streaming through your body, billions of them per second, throughout the course of your lifetime, only maybe a handful of neutrinos will actually bump into one of the atoms in your body. Put another way, if you were to shine a beam of neutrinos through a block of lead 1 light year thick, more than half of them would pass through unscathed. And yet so many neutrinos are released in a core collapse supernova that the neutrino flux would literally kill you before the flash did. Just phenomenal stuff to think about. So the shock wave, now it propagates out, sweeps up its own mass, and then briefly stalls for about a fraction of a second. And neutrinos are pouring out of the core. Now, normally they would stream through normal matter unscathed because they're so weakly interacting. But this collapsing core is on the order of the density of atomic material. So these neutrinos that are streaming out of the core ram into this material, and it looks like a brick wall to the neutrinos. So the neutrinos get absorbed by this atomic nucleus dense material. It begins to heat up, sending violent pulsations, if you will, were through the core. And then 300 milliseconds later, the shock wave refreshes and reignites. It ignites a blast wave through the star that is the cause of explosive nuclear fusion, which accelerates the shock wave even more as it heats and accelerates. And a few hours later, it breaks out of the surface of the star, ripping the star apart. And by the time it gets to the surface of the star, it's traveling at 1/10 of the speed of light. Remember, we're talking about a red supergiant star here, 5 astronomical units. So it takes us years to get to Jupiter, took us 7 months to get to Mars. Now imagine making that same journey in only a few hours, moving at 1/10 of the speed of light. That's the speed of a shock wave when they in a type 2 supernova as the core collapses and rebounds. So the result is a supernova. And the luminosity rapidly ramps up in only a few minutes to about 10 billion solar luminosities. Put another way, a supernova can briefly outshine an entire galaxy of stars. And here you can see the supernova from 1987. And this was a really famous one. I did a talk on this one a few years ago for the 30th anniversary. One of the most studied supernova because it went off in the Large Magellanic Cloud, not our galaxy right next door, but very interesting, the closest supernova that was observed in our lifetime. Now the blast wave can result in ionized gas that lasts for a few thousand years after the explosion. That's essentially what the Crab Nebula is. It is the remnant of a massive star that underwent this process. And interestingly enough, the shell is actually still expanding today. So let's see if I can, let me see if I can show that here. Here you can see a decade-long time lapse of the Crab Nebula from 2008 to 2017. And you can actually see 1,000 years after this star exploded, the shell is still expanding. Pretty cool stuff. Now, the blast wave has another significance. It builds the periodic table. The first 5 elements of the periodic table were cooked up in the first 20 minutes of creation. To get from element 5, boron, to carbon, we got to wait millions of years for stars to form and for carbon to be cooked up in the cores of stars. And of course, the process I just described gets you up to heat, to iron and nickel. A supernova blast, the shock wave now will release iron, and this iron that is blasting out from the core slams into the neutrons that were released during photodisintegration. And as a result, I can now literally blast my way up to the rest of the periodic table. So I get from iron all the way up to basically the purple realm right here. That is the shock wave of the supernova, resulting in heavier elements being built in the periodic table, because I now have the neutrons released from photodisintegration and the iron from the blast, as well as plenty of energy to work with. So that is how we build, or that is how supernova, if you will, build all of the elements in the periodic table. You've heard this line before. We're made of star stuff. The calcium in your bones, the iron in your blood, and the rare earth elements, if you will, in the microchips that are being used in your computer and your cell phone were cooked up in massive stars that went through this process and exploded their chemically rich guts into the interstellar medium, and then seeded the medium, if you will, for the next generation of stars. So to kind of finish up here, I'm just going to show you a quick video of the Crab Nebula through my 10-inch Dob. And this was taken a week ago. It's cloudy tonight, but we had clear skies a week ago. I like a 10-inch because it's very budget friendly. What's not budget friendly is the night vision eyepiece connected to an iPhone, but it gives you an idea of what you would see through the telescope. So here's footage unedited from a week ago.
All right, there it is, Crab Nebula. See how much footage we can catch before it actually moves out of the eyepiece. Supernova remnant, visible naked eye in 1054 by the Chinese. This, of course, is a type 2 supernova, meaning it's a massive star like Betelgeuse. Oh, we had a jet go right across. Man, a jet went right across the eyepiece. You talk about a huge bonus right there. Wow.
Extra credit.
That's fantastic. We saw a jet fly right across the eyepiece. Unbelievable. All right. And of course, you know, you got to move the telescope to get it back into focus. There it is. Got about a minute of footage. Crab Nebula, supernova remnant. This might actually be the showstopper right here. About a minute worth of content. You can see this thing moving. You can actually see, because it's a Dobsonian and it doesn't track. You just capture it, and you can actually see it move. You can see the Earth moving. So that's some pretty cool stuff right there. Wow, look at that. A little over a minute of footage right there. I can just kind of talk through it. That was really something. You get a jet going right through the eyepiece. March 6, 2021. Burton Sugar Farm, Crab Nebula, supernova remnant.
We had a question earlier about UFOs. You never know what you're going to see in an observing session. So alcohol is strictly prohibited at our observing sessions, and I'm not a big drinker myself, but you get 3 guys in a still, you'd be surprised what you can see. So anyway, when will the next supernova occur? That's the $1 million question. We're overdue. It's been 400 years. And one star we're keeping an eye on is Betelgeuse. And of course, if one goes off in our backyard, how bright will it be? And could it possibly alter the ecosystem of Earth? If you're interested in learning more about Betelgeuse, and it made the news about a year ago, and it was featured on the cover of Sky and Telescope magazine for the great dimming that occurred a year ago, the guy who wrote this article, Tom Calderwood, is going to be speaking at the Memphis Astronomical Society next month. That's April the 9th. If you would like to receive a notice on that, just go to the website joinmas.com. We'd be happy to add your name and email, and we'll send you a notice. And of course, we'll also post a presentation to our YouTube channel as well. So that is it. I'll turn it back over to Billy, see if there are any questions.
All right, well, thank you very much, Jeremy. So my question is, how much did you have to pay the pilot to fly by the Crab Nebula at the precise time?
Yeah, exactly. If I was an astrophotographer, I'd probably be swearing because it just messed up my shot. But
Yeah.
if you're viewing through a telescope, it's kind of cool to see that sometimes. You
Yeah.
never know what you're going to see.
We did have one question. Do you have any information about how long the supernova was reported to be visible to the unaided eye, especially like during the daytime?
During the daytime, it was a couple of weeks, I believe. As far as being visible to the naked eye, a couple of months, and then it rapidly fades after that. So it's, it ramps up, the light curve, it ramps up rapidly, and then it slowly decays. So it's only naked eye visible for maybe a couple of months before it fades away.
Gotcha. Okay. I don't think I see any other questions at the moment, but we may get a few others as people are still digesting everything. So thank you very much. Very informative.
Thanks.
All right, and so our final speaker for this evening, we're going to head out of Tennessee and out of the country and go up to Montreal, Quebec, Canada, and visit with Simon Guichendu, who is a PhD student at the McGill Space Institute. So he's going to also give us a little bit more information about those really interesting little objects at the center of these supernovae remnants like the Crab Nebula. So Simon, let's go ahead and take it away there.
Well, thank you so much for the introduction, Billy. Hi, everyone. I'm very happy to join you tonight from the International Space Station, which is much more interesting than my living room. And I want to talk to you all about my favorite object in the universe, and that's neutron stars. So let me share my screen. A quick check. Can you all see this and my cursor? Okay. So let's go back to the Crab Nebula that Jeremy just showed us. This amazing image taken over several years of the nebula expanding, but now I want you to look closely here in the center. And maybe you can see that there's this sort of twirling gas motion that we can see. So my question to you is there anything in here? And it turns out if you look with the appropriate instrument, there does seem to be something in there, something that's blinking. This animation here is slowed down by a factor of 100. So in fact, this is blinking very, very fast. It's like the universe is winking at us, telling us that there's some mystery to solve. And we're going to solve this mystery tonight. And to do that, I want to take you back in the history of science. I want to take you back 100 years to the beginning of the 20th century. The early 1900s were a very interesting time for physics. On one hand, you had physicists developing quantum mechanics, telling us that matter on very small scales behaves probabilistically. So the particle can be here or it can be here, and there's some probability for both. Very weird stuff that still today we don't fully understand. And just to set the stage, there was this gentleman you might have heard of, Albert Einstein, who in 1915 developed the theory of general relativity, telling us that space-time is curved and that gravity is nothing more than mass bending space-time. So he wrote those equations, and just a few months later, this other physicist, Carl Schwarzschild, was on the battlefield of World War I, and he was the first to solve Einstein's equations for a simple mass that is not rotating, not moving, and just what is the curvature of space-time around that. Unfortunately, he died of an illness only a year later, so he never really got to witness how important his work was. But as people started looking at his work, they found that there was this weird thing about his solution. There's this point, we now call it the Schwarzschild radius, where it turns out that if you take all of the mass, let's say, of a star, and put it inside of the Schwarzschild radius, you would form this event horizon where if anything crosses the event horizon, including light itself, it would never come out, almost like a black hole in space-time. But they said, okay, you know what? This is probably just a mathematical artifact of Einstein's equations. Surely nature will never allow such things to happen because nature will not allow objects to become so compact. Well, anyway, that's a story for another time. We jump forward 15 years, and some other different groups of physicists were trying to discover new particles. They were shooting some particles at sheets of metals like gold and platinum and seeing where they bounce off. And in 1932, James Chadwick discovered the neutron in this way. And that was very good because with the neutron, they were able to explain how the nucleus of an atom can remain stable. So that was good. And then back to astrophysics, just 2 years later, these two astrophysicists, Fritz Zwicky and Walter Bade, said, well, actually, we can use this neutron to explain supernovae. Because see, the thing about supernovae is that they're really bright. We know that from the last talk. But in fact, they're so bright that physicists couldn't figure out how it was even possible to produce so much energy. And what Zwicky and Bade suggested is that this energy must come from the gravitational collapse of a massive star. And that gravitational collapse will release all of that gravitational energy by making an object that's very, very compact. But that's only possible with the existence of the neutron. Let me show you why. We're going to go into the core of a star that's about to collapse. So as you learned in the last talk, stars burn hydrogen to make helium, helium to make carbon, and so on until you're left with a bunch of iron. There's some other stuff, but let's just keep this picture simple. So the star has made a bunch of iron, and the iron will not fuse anymore, right? So it can no longer sustain its own weight, and it will begin to collapse. So the star collapses. This is the core. Okay, but eventually the iron atoms are too big, so we keep collapsing, and they're just going to break apart into their more fundamental particles, protons and electrons. We keep collapsing, but there's a problem. Remember, electrons and protons are charged, which means electrons repel each other and protons repel each other. So we're trying to collapse this gas, this soup of protons and electrons, but it's resisting. But fortunately, the neutron exists. And Zwicky and Bade's idea was exactly that the protons will absorb the electrons to create neutrons. Okay, and neutrons don't have a charge, which means we can keep collapsing further. There is a limit, however. Eventually, if you take a bunch of neutrons and try to bunch them together really tightly, there is a limit, a fundamental quantum mechanical barrier that says no more, you can't go further. And that is when the bounce of the supernova happens. So that was their idea for how supernovae can have this much energy. But you have to realize that in the 30s, it wasn't common to combine small-scale physics like quantum mechanics and particle physics with huge, large-scale astrophysical phenomena like stars. And so their idea of the neutron star was very controversial at the time. And when I was browsing online for some pictures of these physicists, I found this funny quote. And it turns out that Fritz Zwicky was not such a pleasant man. And he said of the scientists who disagreed with him that they were scatterbrains, sycophants who publish useless trash. So he was correct. Neutron stars do exist, and they are the result of supernovae, but I don't know about his methodology to convince his colleagues. Anyway, for now, that was just a theory. We jump forward 30 years to a much more pleasant scientist, Jocelyn Bell Burnell, who at the time was a PhD student at Cambridge in the UK. And her advisor were working on this, building this radio telescope. And this doesn't look like a radio telescope, right? It's not a huge dish. It's just a bunch of wires, but in radio that works. And what they wanted to observe with this radio telescope was actually quasars, which are centers of galaxies that are very, very bright in radio. That was the object of their study. But what they found was something different, something a bit strange. One day, Jocelyn Bell Burnell went to her telescope, and the way it worked is that the array was connected to a needle, which would draw on paper as radio intensity was picked up. And what she found was these pulses, these very regular pulses that were separated by 1.3 seconds. And that was weird. Their initial reaction was that of being very skeptical. Maybe it's interference coming from somewhere else, because something you need to know about radio observations is that they're notoriously very difficult to do on Earth. And that's because as humans, we make a lot of radio waves. It's even worse today with all our cell phones and Wi-Fi. It's very difficult to observe the sky in the radio. There's even a funny anecdote of a physics group that found this weird radio signal in their data. And throughout the week, it became clear that this radio signal was happening every day around lunchtime when someone was using the microwave. So you really have to be careful with radio data, but Jocelyn Bell Burnell was very thorough in her analysis to try to rule out any other thing that could happen. And she went back every single day. And what was interesting is that these pulses were happening every day at the same time. And with that, it sort of makes sense that the signal is probably coming from the sky, because this radio telescope is not moving. But as the Earth rotates, it looks at different parts of the sky. And every day, say at 2 p.m., she would see these pulses. So it made sense that this was a new kind of, at least something coming from space. And as the story goes, they initially called this source LGM1 for Little Green Men 1. I don't know how serious they were about that, but maybe it was aliens trying to communicate with us. But then they kept looking in the years coming, and they found other pulses like this from different parts in the sky. So pretty quickly, it became clear that these pulses were a new kind of astronomical source, a new kind of pulsating star, which they called a pulsar. And just a quick aside, those of you familiar with music from that era might recognize this album cover. It's an album cover of Joy Division. And what you're seeing here is these pulses from that first source that Jocelyn Bell Burnell discovered. So in the years after this first discovery, it became kind of obvious that pulsars were most likely the neutron stars suggested by Baden's Vicky. And I want to sort of take you through the reasoning as to why we're so sure of that. So let's say you've just heard of this new pulsar, you know it's from space, and you're trying to imagine what source in space can produce these pulses. So what do I need to make a pulsar? The first thing I need is a large reservoir of energy. So Jocelyn Bell Burnell was going back every day. These pulses were not stopping. They kept having the same intensity. So for all of this radio light to be produced and get all the way here on Earth, you need a large reservoir of energy. So this is probably a star. The other thing you need is some way to make radio emission. So stars like the sun do produce radio, but most of their emission is instead in the ultraviolet or visible light. So to make all this radio emission, there has to be some way to produce it. We'll get back to that later. But the third and most important ingredient you need, of course, is a way to produce extremely regular pulses at different frequencies. And really, when you get down to it, the only way to make such regular pulses is with the rotation of the star itself. But that rotation to produce pulses at such high frequencies needs to be extremely fast, right? The sun doesn't spin around itself every 1 second. So how is that possible? Well, let's go back to high school physics or college physics and talk about conservation of angular momentum. You're all familiar with conservation of linear momentum from everyday life. Let's say you're playing pool and you shoot the white ball directly onto the red ball. The white ball stops, and then the velocity of the red ball after the impact will be the same as the velocity the white ball had before the impact, right? That's conservation of linear momentum. Conservation of angular momentum is the same thing, but for rotation. And the typical example is that of the ice skater. So as the ice skater spins around with her arms extended, when she brings her arms closer together, we say she reduces her moment of inertia, which means she must spin up. She must accelerate the velocity of her spin to conserve angular momentum. Okay, let's do the same thing for a star. Let's take the sun, which has a radius of about 700,000 kilometers. I realize that's not the unit of distance most of you use probably, but it's also a lot of hundred thousands of miles. And the sun spins around itself once every 25 days, something like that. If I do the same thing, I take the sun and I make it very, very compact, into an object with a radius of about 10 kilometers, if I want to conserve angular momentum, this new object needs to spin around itself every 0.5 millisecond. So there we go. With conservation of angular momentum, I can take an ordinary star, and if I can make something very compact out of that, like in a supernova, a core collapse supernova, I can get these pulses that are very rapid. So now I take you to the current model for what a pulsar is. A pulsar is a rotating neutron star. And then the last ingredient, remember from the previous slide, is that you need some way of producing radio emission. And for reasons we don't fully understand, pulsars have very, very strong magnetic fields. That's the blue lines you can see here. So you don't actually see magnetic field lines. That's just an artist's impression. But when you have such strong magnetic fields, when particles accelerate along these lines, they will emit radio photons. So these cones, these two pink cones you can see here, are the cones of radio light. And you'll notice that these cones are misaligned with the axis of rotation of the star. So here's another animation. The two yellow cones here are where the radio emission is emitted. And what's happening is that when the cones pass in front of Earth, that's when we see the pulse. That's what the pulsar is. So it's not that the radio emission is going on and off, right? It's just that the star is spinning and the cones are pointing towards us and then away and then towards us. So that's what pulsars are. And that was really a groundbreaking discovery in the field of astrophysics. So important that Jocelyn Bell's advisor received a Nobel Prize in physics, even though she made the discovery. So good for him, I guess. Okay, moving on. It's been about more than 50 years since we've associated pulsars with neutron stars. And I want to tell you a bit about what we know about these neutron stars. So as I told you, they're very compact. They have about the mass of the sun, a spoonful of this neutron star. That spoonful would weigh as much as all of the humans on Earth, all 8 billion combined. Pretty crazy stuff. And it's spinning at the speed of a kitchen blender. It's a pretty scary sight. In terms of their structure, it's pretty interesting. It's not like most stars. It has these layers. So on the outside, it has a crust made of mostly hydrogen, helium, some other ions. And then we transition into a mantle, where in the mantle you have neutrons behaving like a fluid, like water. Transition into an outer core and then an inner core. And really, we don't know what's going on in the inner core. But that's an active research area today. And then there's this other thing I want to tell you about is that in the transition between the crust and the mantle, where you have a bunch of ions, protons, neutrons crushed together at higher densities, we think that some strange phase transitions occur. You begin with this gnocchi phase, where you have some bunches of about hundreds of protons and neutrons packed together into these gnocchi-like shapes. You keep crushing, keep going deeper into the crust, and the gnocchis get together to make this spaghetti phase. Keep going, you get this lasagna phase. Eventually you get anti-spaghetti, anti-gnocchi. You think I'm joking. I'm not joking. This is from an actual real scientific paper from 2017. So neutron stars are absolutely crazy. These kinds of things we could never produce on Earth. So in a way, they're kind of like our laboratory, but in space. So how am I doing for time?
Oh, we're at about 9:10, but no, I mean, please continue.
Okay. There's one more thing I'd like to tell you about. We're going to change context a little bit. So the pulsars that we've talked about so far are what we call isolated neutron stars, meaning they're basically alone in their environment, or at least they're in their nebula, but there's no other stars around. There are different kinds of systems, which we call binary systems, where a neutron star could be in a binary orbit with another star. So they're spinning around with each other. And some pretty fun things can happen in these systems as well. For example, here we have a red giant. And over the course of its evolution, as Jeremy told you, it's going to grow. And when it's in a binary with a neutron star is very, very heavy, right? It's small, but it's still heavy. It can grow to such a large radius that matter on the outside of it, just all of this gas, can become more attracted to the neutron star than to the main star itself. So just so you know, we call this the companion star. We call this the accretion disk, because what happens when matter is more attracted to the other star, it's going to start changing. It's going to start accreting onto the other one. It basically says, I'm no longer with you. I'm going to see this new neutron star. So you form this accretion disk. You have some jets because matter is funneling in, but some of it is going to be ejected. And the neutron star is here in the center. Here's another animation you can see of an accretion disk forming. So this is the red giant. This is the neutron star here in the center. And you have this accretion disk that forms and this emission in jets. So pretty cool stuff. And just to close it off, what happens when you have matter into an accretion disk funneling itself onto an object that's already very, very dense? A rhetorical question you can't answer, but what do you think is going to happen? Something's got to break. This neutron star is already too massive, too dense. And what happens is that all of this gas that's building up on top of the crust, all this hydrogen and helium, is going to eventually fuse as it does in the center of the sun, for example. But that's going to happen very, very quickly because of the extreme conditions that this star is in. And what's going to happen is a massive explosion. It's called an X-ray burst, where in the span of a few seconds, the whole surface of the star is going to burn by fusion. All of the helium will be turned into carbon, and a bunch of X-rays will be emitted. And these things are very, very bright. I have a few examples here. 1 second. These are some actual data of X-ray bursts. So to see these things, it's not visible. You can't see it by eye. It's an X-ray. You need an X-ray telescope, which are in orbit around Earth. And so this is time in the x-axis in seconds, and this is luminosity. And I haven't put the units here, but let me just tell you, 1 tick here in the luminosity axis is equivalent to 100,000 times the luminosity of the sun. These things are crazy bright. Not as bright as supernova, but still pretty exciting. So what these look like is a very quick flash in a few seconds, and then a peak, and then a long decay. But there are some other kinds. For example, this one, the whole burst lasted almost an hour. And these are also a very active area of research, because with these bursts, we're able to study the neutron star directly because it makes it very bright. And there's a lot of effort going on to observe these. Here's one telescope that was launched in 2017. It's called the NICER telescope, and it sits on an arm outside of the International Space Station where I am. And so it's like here or something. And the whole purpose of this thing is to look at neutron stars directly and also observe these X-ray bursts, which is what I work on for my research in Montreal. So that's all I have. If there are any questions, I'd be happy to answer.
Thank you very much, Simon. Yes, actually I do have a few questions. So would these X-ray bursts be considered a nova?
Oh, that's a good question. They're not called nova, no. It's a different category.
Okay.
And there's no chance that some astronomers 1,000 years ago will have seen them because, again, they're an X-ray, so we don't see them by eye.
But kind of related to this, and this may go back to Jeremy's presentation as well. Let me find it here. What are more common, supernovae or just novae? And do novae have enough energy to create elements past iron?
Well, novae is kind of a generic term. So one other type of novae that I can tell you about is a similar thing to what happens here, but instead of a neutron star being there, it's a white dwarf, and it's a similar thing. You have a thermonuclear reaction occurring at the surface, and these are called classical novae, so they would fit into your novae question. And these can happen very regularly at every few days or so. So they're much more common than supernova. And what was the second part of the question?
And those could lead up to the type 1A supernovae that Jeremy had.
Exactly, yes.
Before. Yeah. Okay. So yeah, the second part of the question was, do novae have enough energy to create elements past iron?
Oh, that's a good question. Maybe Jeremy would know this better than I do. I think they do produce some elements, but it's not nearly as much as supernovae. It's quite negligible compared to supernovae. What do you think?
I think a nova is just a burst from the surface of a dense nugget, like a neutron star or a white dwarf, as a result of accreting some extra mass. So take a white dwarf, for instance. You put a little bit of extra mass on there, and then you have a phenomenon resulting in a nova. I don't think it really builds any additional elements. I'd have to research that further also, but it's really just a flash, if you will, from a star accreting additional mass, but not a detonation like a supernova.
Yeah. So in these X-ray bursts that I showed you, in the case of a neutron star, some elements heavier than iron are being produced, but they're not ejected. They remain, they sort of bury into the crust of the neutron star. So those are not the ones that we end up with on Earth.
Okay. Yeah, the novae, like when you have a white dwarf, we can get material spilling in onto that white dwarf, and you get a layer of hydrogen and helium, and then eventually, when enough of that material falls in and there's enough pressure, it gets heated up to fusion temperatures, and so all of a sudden you'll get a burst of hydrogen fusion on that star, and which could leave behind a little bit of material to gradually add to the mass of that white dwarf. And one thing about white dwarfs is that they have an upper limit to their mass. So if they get to approximately 1.4 solar masses after these repeated novae leave behind a little bit of material every time, then that's when gravity is able to overcome what's called electron degeneracy pressure. And at that point, so that's what's keeping that core from collapsing down even more. But once you surpass that, because you've got too much mass and too much gravity, then you get the star trying to collapse down and heats up tremendously fast and tries to fuse all at once and basically blows itself apart. And so that's when you would have that type 1A supernova. So we were talking about the different rates at which these pulsars are rotating. So I think it was the Crab pulsar spins around 30 times a second. Do you know what the fastest pulsar is that we know of?
Oh, I think it's just below 1 kilohertz. So it's many hundreds of hertz. So let's say, I'm not sure the number exactly, but let's say 700 to 800 rotations per second.
Wow. Yeah,
these are called millisecond pulsars.
Yeah, it's just mind-blowing to think about something that large spinning that fast. I mean, it would just be a total blur. We wouldn't be able to see the surface at all. Wow.
Yep.
What is the process of matter being ejected? So I think here we're referring to the jets forming. Why do those jets form?
Oh, yeah. Here, for example. So that's first of all, this is not unique to this system with a neutron star and other star. This also happens in around black holes, when black holes are accreting, and it's not perfectly understood, but essentially this accretion disk has a lot of angular momentum, and it can't suddenly transfer all of the matter to the surface of the neutron star or inside the black hole. Some of it in the process will be ejected. It'll sort of be blown away into these jets.
And I think
that's the general idea.
Like stars forming, they'll also form these jets, and that's where it's thought there's a lot of, because the material in the disk is getting heated through friction, it creates magnetic fields, and that swirling material kind of creates basically a swirled magnetic field, and so that hot ionized material gets caught in that and gets shot out too. So is that kind of similar to what's going on here as well, or could be?
Yeah, certainly the magnetic field plays a role. When the magnetic field is strong enough, in fact, it will guide the accretion. So right here at the inner edge of the disk, it's not going to fall directly onto the equator of the star. Instead, it's going to be guided by the magnetic field and fall along the poles of the magnetic field. And in fact, sometimes we can see that as hot spots on the surface of the neutron star.
Interesting.
So you can imagine sort of standing on the near the magnetic pole of the neutron star and seeing these huge columns of gas falling and making this very, well, probably don't want to stand there once again, but you can imagine the way the infall happens.
Right. And basically it's getting shock heat as it slams into the neutron
Yeah.
star. Okay.
Exactly.
Let's see. I think there was one other question about, for this particular part, does our sun emit neutrons or X-rays, and will it go nova someday?
Does our sun?
Yes. Does it emit neutrons or X-rays?
Okay. It doesn't emit neutrons. Neutrons are like heavy particles. It emits light and neutrinos, and it will not go nova. It's not massive enough. So instead, it's gonna, when it burns out all of its helium, it's just gonna decay into a white dwarf. So it's a more peaceful death, and that's billions of years away. Don't worry about it. But no, it will not go nova. It's not big enough.
Yeah, and our sun does emit X-rays, but
X-rays,
thankfully our atmosphere is really good at absorbing those, so it's good for life. It's bad for astronomy, but at least it's good for life, right? Let's see. I think that's all we had for this particular part of the program. So thank you very much, Simon. I learned a lot there.
Thank you.
So I'm just going to open it back up. We had a couple of other questions just from throughout the program. So I just wanted to address those before we wrap up for tonight. So I'm going to, just welcome everybody to jump in here. And, folks that are watching, if you all have any other questions that you can think of about anything that we've spoken about tonight, or maybe it's not even something we've spoken about tonight, please feel free to pop those up there. So going back more towards the beginning of the program, Adam, when you were talking about the sun at noontime, it's reaching the meridian, we had a question about, is there basically like an equivalent at midnight? So, so we're talking about 12 noon or 12 p.m. for noon, but is there anything special at 12 a.m.?
Not that I can really think of. And by the way, Billy, we can't see you. We just have a.
Oh yeah, that's interesting. Hold on a second.
It's in the notes. I just thought I'd let you know.
Oh, sorry. Yeah, I don't know why I've dropped out there. Let me try.
Not that I can think of. I mean, if there is, and I'm just mistaken, somebody else, please chime in.
No, I agree. There really is nothing that describes a line going from north to south through the point under your feet, the nadir. There's nothing like the meridian for the flip side.
Right, and the meridian, and that the concept of telling time is based on the sun. So you got to see it. So it's during the daytime, and below the earth just was nothing. It was just down there. So I say, I guess no is the answer.
Okay.
Maybe we should create something like that, and we should name it after someone here. I don't know.
Sounds like a plan. Yeah, I'm not sure why my video isn't working, but oh well, I'll just put up a still picture of me so everybody knows what I look like there. Let's see. I know I had another one here. Sorry. Oh, there was a question early on about how are we able to predict eclipses so accurately?
I'll try and tackle that. So we have a really good understanding of how things orbit other objects. So how the moon orbits the Earth and how the Earth orbits the sun. We really understand that physics, and that's mostly thanks to Isaac Newton, who gave us the calculus and also gave us the equations that describe orbits. So we can predict where the moon will be 20 years from now or 2 days from now, and where the Earth will be and where the sun will be. And that allows us to predict those eclipses with great accuracy.
Yeah, I just want to add to that just how remarkable it is to live in these times. Newton's laws of gravity work so well and are so precise that we can send a space probe billions of miles to the outer solar system to fly by Pluto in 9 years and miss it by about the distance from where I'm sitting now to the end of this room. And I'm in a pretty small room. That kind of precision as a result of the laws of gravity is just inconceivably remarkable in comparison to thousands of years of human history. We just landed on Mars. People take that for granted. Imagine standing in New York City and throwing a basketball toward a hoop in Los Angeles and hitting nothing but the bottom of the net. That's the equivalent of what NASA accomplished mathematically and theoretically by landing Perseverance on the surface of Mars. We truly live in miraculous times.
All righty. Well, thank you, everyone. I'm not seeing any other questions at the moment, and we are getting near 9:30. So, well, I think with that, I would just like to thank everybody who presented tonight. So Adam Thans from Bays Mountain Park and Planetarium, Jeremy Bellman with the Memphis Astronomical Society, Dr. Ann Viana, who's also with the Memphis Astronomical Society, but also Rhodes College, Theo Wellington from the Barnard Seaford Astronomical Society, and then Simon Gishindu from the McGill University up in Montreal, Canada. So also want to thank everybody who was viewing tonight. I think we had a great program. Thank you for submitting the questions. And if you have any other questions or suggestions for future programs, please don't hesitate to email us and let us know. And also big thanks to Helen Morissette and Brian Smokler for helping make this night possible. So with that, I think we will I'll bid everyone farewell for the evening. Hope you all have a great rest of the weekend. We're going to be doing something in April for another virtual star party, and we'll be sure to post information on our website in the coming days. So everyone have a great weekend.